Whenever you are setting up the large language models for actual applications, you generally have two main components to kind of consider. One is the engine and one is the server. So engine actually manages the LLM, the core part of it, taking care of like processing the incoming request, boosting the efficiency, getting the multiple requests, putting them in the batches to kind of before the processing. And this actually adds up to the speed times significantly, the speed response times. And then you have the server, which is in between, and then it receives the request from the user, sends it to the engine for the processing, and then delivers it back. So this is what happens in the LLM inferencing phase. Now, there are different approaches that you can deploy the LLMs in production. One of them is OpenLLM, one is vLLM. There is Hugging Face, which is there. You have RayLLM. So there are different techniques out there. And what we are going to discuss in this particular video is about vLLMs, how they are kind of different and what value they add over the other ones. And then we'll try to actually deploy it onto a Kubernetes cluster, which is bound by GPUs. So it should be exciting. There should be demo, and we'll have a lot of things getting hands-on to make things work. So let's first try to understand what exactly vLLM is. And for this, I have my friend John who will be explaining what are vLLMs.
So yeah, what is vLLM? That's a great question. It's a inference engine that can run large language models like Llama 3 or one of the Mistral models, and primarily is a Python library. I think that's the main way that people interact with it these days, but has a lot of really incredible capabilities for fast performance on GPUs, as well as being able to serve an OpenAI compatible API to many, many clients. Some of the magic that makes vLLM really, really great is something called paged attention. And this is really a more sophisticated way that the large language model can manage the memory on top of the GPU. In short, it's basically a way for it to do more efficient memory management of its key value store as it's doing completions, as it's doing inferences, which is really just a fancy way of saying it's more memory efficient. Thus, it's faster, and therefore it can serve more clients from its API. So this makes vLLM a really, really great choice if you want an OpenAI compatible API that you can serve to clients to do inference and text generation.
Awesome. Now that we know vLLM, I think it's important to know how vLLMs are different. So let's get into that.
vLLM is different from some of the other inference engines, primarily in that it's a Python API that you can provide to other Python applications, or even provide as a container within a bigger orchestration of something that you might be trying to do with microservices and stuff. Something like llama.cpp is a C++ library, or I guess a C++ binary that you can compile down to then run inference on models from that single binary. So there's a little bit of a difference there, where that C++ application, llama.cpp, has a bunch of dependencies and then compiles down to a single interface that you can interact with, where vLLM is a library. Another big difference in this sort of ecosystem is that vLLM does a really good job of interacting with and managing your GPUs that you might have in your cloud instance, or even on your local workstations. Further on that thought is that vLLM does really, really good at using multiple GPUs and balancing loads across all of them within your compute instance. So maybe you have a cloud compute instance with a couple T4 instances, which are pretty good GPUs for doing inference. You could use all those T4s across your vLLM running on your compute instance, and they would all be balanced and managed correctly by vLLM and by the library. So you would get very good usage out of your GPUs on vLLM.
Well, those were some amazing differences on how vLLM is actually different. So now let's dive right into the demo without wasting time.
One of the other main differences with vLLM is that it's currently only supported on Linux as of the date of this recording. So what that means is that getting this to run locally on your MacBook or on Windows is a little more challenging because of its specific target at running production loads on Linux servers. So if you were on a Linux machine, you could run this locally or develop your Python application against your NVIDIA GPUs on your Linux box by just doing a simple pip install vLLM. Doing that will install the libraries to get you going with your Python application. Another way to do this locally on your Linux application box would be through the Docker container. And the Docker container would give you some good capabilities to run this not only in a container orchestration setting, but on top of your local hardware as well. So let's take a quick look at what that would look like. So this command here is a Docker run command from the vLLM documentation. We call Docker run. We give it a runtime. If I had an NVIDIA GPU on this box, it would use that NVIDIA GPU with the NVIDIA runtime. And then I could give it the GPUs all command to consume all the GPUs running on this box as well. A couple other things with the cache. We're giving it the Hugging Face cache on this machine, the Hugging Face token, so that it can pull models from Hugging Face like the Mistral model or the Llama 3 models that you've been given and granted access to. You'll need that Hugging Face token when you run your container as well. We then very importantly have the port exposed, which will then expose that OpenAI compatible API. Then we ensure that we're running on the host machine network. And then very importantly, the vLLM OpenAI Docker container. And then finally, the model. And this one, in this example, is using one of the Mistral 7 billion parameter models. So up in the cloud, I actually have vLLM running on a very small container on a Linux box with a GPU. And inside of this box, the port 8000 is exposed, giving us that OpenAI compatible API from vLLM. So if I curl localhost 8000, that will give us the detail not found, which is just the basically not found 404 route on the root of this. So now what I want to show is a more full, complete curl command here. And you'll notice that this is hitting HTTP localhost 8000, which is the vLLM API server, on the v1 completions route, which if you're at all familiar with the OpenAI API, you'll know that that's the API from OpenAI that does completion inference on some prompt. The biggest difference here is actually that we give it a different model. We're not giving it a GPT model, but rather we're giving it one of the Hugging Face models from that we've pulled down already on this machine when we bootstrapped and started running the container locally. You'll remember that -- model flag when we showed the Docker command, which will actually pull that model down from Hugging Face and have it on the machine and ready to do inference through vLLM. So the model that I have on this machine right now is one from the Bloke, which if you don't know, the Bloke used to provide quantized models, which this is an AWQ quantized model, which really is just taking the very large floating point precision numbers inside of the model and just kind of truncating those down a little bit so that they can run a little more efficiently on less powerful hardware. So maybe in some quantizations, it takes it down from 32-bit floating point precision all the way down to just 4-bit floating point precision. But it varies. It varies from different quantization techniques. But this one is an AWQ quantization from the Bloke. And the prompt that we're giving it is San Francisco is A. And then we're going to expect it to actually do some chat completion inference. And we can actually give it some more tokens to do. Let's do 300. It's going to consume that from its API, and then we will actually get an inference here. So here we could see the inference for the prompt San Francisco is, and we could see that it started with a city known for its beautiful weather, diverse population, and iconic landmarks, etc., etc. So this is actually the full returned OpenAI-like JSON that you would get from the OpenAI API. And really, this is sort of the beginning of what you can start to build a bigger service on top of using vLLM. If I was to hit vLLM multiple times with many different curl requests from many different clients, this container running on this machine would be able to service those through its batching and through its OpenAI compatible API. One other thing to mention before we move too much further about running the container for vLLM is the specific drivers to your system or where you're running vLLM. In this case, this Docker run command that I showed, we are doing the runtime NVIDIA here, and you need the NVIDIA drivers installed on your system or maybe installed onto the nodes on your Kubernetes cluster or wherever you have this going, just so that it can actually use the CUDA cores from the NVIDIA GPUs on that system. So if you're going to use the NVIDIA runtime with NVIDIA GPUs to take advantage of the very powerful CUDA cores to do inference, you need the NVIDIA drivers. vLLM also provides ROCm runtimes, which you can then install the AMD drivers and use those GPUs, and even on CPU runtimes if that's what your hardware can provide for you. The library is very flexible, and through the container here, providing an OpenAI compatible API, it is also very flexible for the various runtimes you may be running this with. So now that we have the capability to run a Docker container and get some inference from that container, we can actually scale that up and look at a real-world use case of this running on Kubernetes at OpenSauce. This whole mechanism of using vLLM and an OpenAI compatible API is what powers our Star Search AI offering and gives us inference and generation on summaries that we do for pull requests and issues from GitHub to then power embeddings and a whole AI product. But let's get into a Kubernetes cluster that we have. I'm going to go into K9s and showcase kind of from start to finish what this actually looks like. So this is a Azure Kubernetes cluster, which this will work just anywhere. But the thing to note here is that I have some GPUs. So if I go into nodes, I have a GPU pool that has a few T4 GPUs that run this and make this possible. Each of those GPUs, and this is again depending on your platform and what GPUs you're using, some platforms or managed Kubernetes services may just automatically do this, automatically install the GPU drivers for you. But if I go into namespaces, I have this GPU resources namespace. And inside of here is a NVIDIA device plugin, DaemonSet. And this DaemonSet is actually what installs the NVIDIA drivers for the pods to be able to take advantage of the GPU on top of what we have on the node. So let's get out of there and then look actually at the YAML for that. And all of this YAML will be a part of a blog post on the OpenSauce site that goes over this in a little bit more detail as well that you can reference. So let's look at the GPU resources YAML. And this is YAML mostly just taken directly off of the cluster. So some of the metadata and stuff you wouldn't want to include, obviously. But we go down to the spec, and we have a few very important bits here. We have a match label selector, which gives us the NVIDIA device plugin, DaemonSet. And then we go a little bit further down. This is where inside of the template, we actually label those as well. So inside of the spec for each of the individual DaemonSet pods, we have the Microsoft NVIDIA device plugin, which this is provided primarily just from Microsoft for AKS. And again, it's all platform dependent. Some platforms may just do this and automatically install the drivers. Go a little bit deeper, we name it NVIDIA device plugin controller. A little bit further down, a bunch of this is metadata we don't care too much about. Importantly, we do have a volume mount where we actually mount onto the kubelet and the device plugins. This is where we can actually drop in the device plugin behind the scenes where NVIDIA is going to give us the driver. A little bit further down, a bunch of this is metadata I don't think we care too much about. Very importantly, we do have a number of tolerations on AKS, and these tolerations actually are giving us the capability to schedule these DaemonSet pods onto nodes that have the GPU, or I guess the NVIDIA.com/GPU taint. So we can tolerate that taint and actually schedule on top of there. A little bit further down, behind the scenes, these are spot instances, which are just a little bit cheaper on Azure, but we also need a toleration for those spot instances to be able to schedule those pods there. And then again, importantly, we have the path to the kubelet device plugins where we actually mount and install, or I guess the pod will install the device plugin for the NVIDIA driver. A lot of this, again, is just taken piecemeal from the Azure example. So make sure to reference your specific platform. But the important thing here is that it provides us the capability to have the driver for the pods that have the GPUs, and specifically in this case, the NVIDIA GPUs. Next, let's look at the actual vLLM DaemonSet that is running to provide on this Kubernetes cluster a internal service for doing inference, again, behind the OpenAI compatible API that it provides. So I have a namespace, and this is vLLM NS, which is obviously my vLLM namespace. And inside of here is a number of daemonsets. And the way I've set this up is to actually have one daemonset pod per node tolerating each of those GPUs, or I guess I should say nodes that have GPUs, so that we can actually have a sort of very well-balanced and spread out usage of our GPUs that we have for all of these vLLMs to take advantage of. So I think there's 10 of these nodes, and there should be 10 or so of these DaemonSet vLLM pods. So let's back out of the cluster again and look at the actual YAML for the vLLM daemonsets. So it should be vLLM daemonset.yaml. And again, there's going to be just a ton of metadata from the actual cluster here that we can more or less ignore. Inside of the namespace, or this is where the namespace that we have it provisioned, which is the vLLM namespace. A little bit further in the actual spec, we have the label selector, and we just have the app vLLM label. And down here is where we actually apply that in the template. A little bit further down, we have the container spec. And this is like very, very important, because this inside of the args is where you're actually going to provide to vLLM, much like in that Docker run command, the actual model. Again, in this case, it's one of the block models. And then also I define the quantization type, which we're just doing half quantization, which is that AWQ here that we define as well. And again, that's just a way to reduce memory usage for maybe some lower level hardware. The T4s that we have here are pretty good. I believe their compute capability is 7.5, if I'm remembering correctly. And using AWQ quantization in this way works very, very well for our use cases. I also have a flag for GPU memory utilization, and I'm setting it a little bit higher, where I'm defining it to use 95% of all GPU memory, just because there shouldn't be, in this use case, any other things running on the GPU to consume memory or any of the resources on the GPU. Definitely tweak these parameters per your use case, per your hardware. It does take a little bit of playing around and just, playing with the knobs to see where the perfect spot is for you. But using more or less all of the GPU memory works very well for us. And then I also have this enforce eager mode for vLLM, which this is a special flag that I believe removes the CUDA graph that it gets built by vLLM, and more or less makes memory a little more efficient to use by vLLM. So there are lots and lots of different knobs and different ways to tweak vLLM in these use cases. And for you, I think it's very, very special to make it work for you and your platform. And that's one of the reasons I really like vLLM, is that it just has all these little knobs to make it work for whatever your use case is. In the environment, we are providing our Hugging Face token, which then it can pull down the models from Hugging Face. We provided the image, vLLM OpenAI latest, which latest is probably not the best or the greatest idea to use, but in this experimental sort of test case, it works very well for our use cases. And then in the ports, we are actually exposing that port 8000, which is the port that gets served for the OpenAI compatible API. A little further down is this special resource limits, which is the nvidia.com/GPU. And this may be also specific to individual platforms, or how your provider or you've set up your Kubernetes to actually provide GPU resources. But through the Azure GPU resources daemonset, it actually gives us the capability to define the number of GPUs that we want to consume by the daemonset and what's available. In this case, there's just one GPU per node, so we can just take the entire GPU when the daemonset lands on that node. A little bit further down, we do have a node selector where we actually select for the specific node with the accelerator NVIDIA label, just to remove any possibility that it may land on any other node type. And then also, very importantly, is a few tolerations for taints. This taint value GPU for the skew is one that I actually added. So maybe it's overkill to have a node selector and a taint toleration for a GPU skew that I define, but it works, and it gives us a little bit more, I guess, fine-grained capability to define where these land. And then that should be about it. So that is really the short and sweet of actually getting a vLLM service running across all your GPUs. Is a DaemonSet where you have tolerations for your GPUs or however you've set that up on your specific cluster on your provider, but then also providing those very important arguments to vLLM to run and do inference on those GPUs specifically. So let's pop out of this again and go back over to K9s. And we can actually look at where we expose this service, selecting these vLLM daemon sets for a service. So if I go to services, in the vLLM namespace here, I actually have a vLLM service. And this, in our use case, is just more or less an internal service. So there's no ingress to this being served out to the internet or to other services on the network, onto VPC. It's only internal onto the cluster, which is probably the most easy, I guess, the easiest use case. But if we describe this real quick and I go down, we can see here the many endpoints that it selects for to then get those vLLM daemon sets. And we can actually look at the YAML to see how that selector works. And let's look at vLLM service.yaml. Again, a lot of metadata because this was just taken right off the cluster. But more or less, the important parts are the ports. So we select the target port 8000, that's vLLM, and then we just expose 80 on the service. And then the selector, where we actually are selecting app vLLM, which is defined in our vLLM daemon set. More or less, yeah, this is a cluster IP, so nothing with ingress or anything that is providing anything more interesting on the actual cluster. But those are the two very important parts of this service, is the selector and then also the port. And then I'll also note that it lives inside of the vLLM namespace, which we'll see when we actually hit this service. So let's go back over to K9s, and I have a test pod that I can actually get a forward shell into. And let me get all nodes and test. So let me get the forward shell here. And this pod can then hit that service, all load balanced behind, good old fashioned Kubernetes service load balancing. But that gives us kind of a single layer where Kubernetes through the services can go and hit the various different daemon sets that are running vLLM. So let me grab the curl command here. And this looks very similar to the curl command we looked at earlier, but you'll notice one thing very, very importantly is different here. We're actually hitting vLLM service.vLLM.ns, which is going to be resolved by Kubernetes DNS. In this case, on this cluster, it's core DNS, to actually hit the v1 chat completions. So this endpoint here will be load balanced across those 10 or so vLLM daemon sets, exposing that OpenAI compatible API. Further down, we can see that we're hitting that same model with Mistral 7 billion parameter instruct. And then this one is a little different because this is actually the chat completions endpoint, not just the completions endpoint, but we're giving it a role of user and some content. And I'm asking it who won the World Series in 2020. Let's see if it actually gets it right. This then will go and hit one of those pods, so one of those daemon sets running on GPU, and then do the inference. And we can see the Major League Baseball World Series in 2020 was won by the Tampa Bay Rays. I'm not actually a baseball fan, so I don't know if that's really true or not. But it did some inference, it did some completion, which is very cool and very exciting. So the other thing to note here maybe is we could do an NS lookup just to show a little deeper on the vLLM service.vLLM ns, and we could see the address that resolves to, and the full DNS name here at .svc.cluster.local. That's some of the magic of providing this OpenAI compatible API behind the internal Kubernetes service. This is used by some of our microservices in cluster that do some database scraping jobs to then go do summaries and some different inferences that power our AI products at OpenSauce. So for you, taking this to the next level, maybe you provide this as an ingress, maybe you provide the service to other internal networks to do similar things on your network or from other microservices. But this gives you that OpenAI compatible API all running on your own hardware via some really, really good open source models that in a lot of ways, in my experience, rival what GPT 3.5 Turbo or even sometimes GPT-4 can do. And in a lot of cases can be significantly cheaper than using OpenAI directly, depending on what types of GPUs you use and what type of load you need.
Thank you, John, for the awesome demo on vLLM and how to use that on Kubernetes, how to use the vLLM library on using Docker, using Kubernetes with NVIDIA GPU drivers that you have, the DaemonSet over there, and then you have a vLLM DaemonSet, and then you have a service. So I hope for everyone who is watching, you now know how to run vLLMs. So vLLM is the library that you can use for LLM inferencing, and it uses a very fancy memory management algorithm called paged attention that John was talking about earlier. So you can use it on your Kubernetes clusters as well. So I hope you learned about vLLM, how you can use it as Docker containers, and how you can deploy in production on a Kubernetes cluster. And there's a link of the blog in the description of the video, which you can do step by step. This works for any Kubernetes cluster. Yes, there are some specifics of installing the GPU drivers separately, which might be separate for each of the Kubernetes clusters, but the vLLM, DaemonSet, and the service should be okay to be used as it is for any Kubernetes cluster. Thank you so much for watching this particular video. Let us know how you do the LLM serving for everyone. Do you use vLLM or you do not use vLLM? And if not, what else do you use? And if you use, what are the performance enhancements you are seeing in your day-to-day production scenarios? And do not forget to like, share, and subscribe so that it reaches, like, more people can use vLLM.